This is a stereo microscope, something I've had lying around for years, but the lights were never good, so I thought it's a great project to put in some of my high-intensity LEDs. In place of the switch that turned on either the upper or lower lights, I put in a potentiometer, which as you go to the right intensifies the upper light, and then swinging to the left intensifies the lower light.
Well, here's a picture of what we pulled out of the microscope. Very good quality ceramic wafer switch, two of these miniature fluorescent lamps, the ballast for each of them, and they were in sockets, and these provided the light for the upper and lower light sources in the microscope. So basically I may keep these inductors, maybe they're handy for something. None of the rest of this, and who uses mechanical switches anymore?
Here's a pile of boards I had made. JLC PCB will make you littles of boards. With their current pricing, I did panelization. I think I got 8 on a standard size panel, 10 by 10 centimeters. So with 5 boards, that comes to 40 of these little puppies. So here's the diagram.
Based on the Tiny85 with, of course, the Arduino bootloader in OptiBoot. Also, when I used KiCad, I modified custom symbols to add the TX and RX lines, so when I'm producing something, I know that those two pins are going to be used for bootloading. So what we have here is a 8-pin connector. A lot of these things are somewhat uncommitted. In other words, this could be pins, they could be vertical, horizontal, or they could be actually tiny screw connectors, depending on the use, since I had 40 of these made. So we have the ground connection. Here's power feed. I don't know, anything up to 36 volts, I guess. 78 LO5 standard 5-volt regulator. Also feed the 5 volts out, which comes in damn handy when you're using the inputs as analog. The reset line has the clamp diode. Probably go into that in a previous video about why you need that on the board. So what we have here is basically 3 input lines. These resistors, like most of the parts on the board, are uncommitted. Depending on your use, you can pick the values that'll work for you. Also, the first one here also has a resistor to ground. What this does, if you want to measure a voltage and it's over 5 volts, you can use this resistor and this one to do a voltage divider. You know, if you make it 5 to 1, then you can read up to 25 volts. Because the inputs will do digital or analog or actually data signals. I've used these to get serial in and out by using bit banging code in the chip here. So I've got 2 outputs here that drive power transistors. They're labeled tip 41. Well, they can be any NPN with a compatible pin out. They can also be Darlingtons if you need a lot more current, or they can be N-channel MOSFETs. I've got some N-channel ones rated at 150 amps. That'll probably blow a trace if I actually try to use it in here. The idea is it's generic, and when I need just a little processing in a project, rather than, you know, screw around with a piece of proto board and solder bridges and a bunch of very ugly stuff I've seen people do, I just pull out one of these boards. I've got about 10 different ones right now, but this is the one we're using for this project here. And this project we're feeding a potentiometer in pin 2 here, and we're doing an analog reading on it. And of course the potentiometer got 5 volts here and ground here it picks up. So that's what's used to adjust the light levels. And then we have 2 LEDs, so we do pulse width modulation in software here on these 2 lines. So, although I think they both actually could run hardware PWM, it just wasn't necessary. I try to do things as simply as I can. Okay, well, here's the software. It's really simple. Now we run almost all of our projects in the classic main style, or as we being called bare metal. Things like direct register access and not using a lot of the C++ extensions, but that's the way I'm used to writing my C code. So basically, we have these two 10-watt LEDs, which we're going to do pulse width modulation to adjust the intensity. So all we have to do is set the output bits, the bits for each one to output, and run through this cycle, which consists of making an analog reading of the potentiometer, which goes 0 to 255. Now, if it's over 130, we do the lamp number 1 and send it a value of the reading minus 128. So it starts, as we just cross the center position, it's at 0 and goes up to 128. If it's less than 122 and we do the other lamp and do 122 minus R, this means as we turn left from center, the bottom lamp gets increasingly intense. Since we're not using the setup and loop functions, we're doing the analog reading bare metal. It takes a whole 4 statements to do it, and there they are. Yeah, I look up in the specs on the ATtiny chip, and they'll tell you what each of these bits do. It's actually pretty simple to do. And then here's our thing that does the PWM. Now it actually only flashes it once. It turns on the lamp, delays microseconds depending on how many we told it to do. Then it turns off the lamp, and then 128 minus width. The width goes from 0 to 127. So, in other words, this one plus this one always equals 128 microseconds. So it's constant frequency. So what happens, scrolling back up here, this loop runs so damn fast that I think we're getting things like 20 kilohertz cycle here, and which gives us PWM. So here's how we did our construction after removing all of the previous circuitry and lamps and stuff. Here's our little utility circuit board here, mounted on a piece of cardboard and then hot glued onto a piece of metal here. After this, I may at least put a couple mounting holes in these. That could be handy, but that works pretty good. Over here is a metal bracket. Now we're looking right at the bottom, and this bracket goes to the 10-watt LED that shines through the glass plate here. The top LED uses the existing wire that goes up this post and shines down from the top. So here the power comes in here. We put a little power jack in, standard 5.5 2.1 millimeter. These are these little strips we make that are nothing but copper circuit board with stripes on them. These replace what used to be terminal strips, if you go back that far, when all the parts in televisions and such were simply strung between terminal strips. Still, it's handy sometimes when you have to join a bunch of wires or mount a large part someplace to use these. So that's what this little guy is. So we got power and ground here. We got a 22 ohm resistor we're using. We don't want to go to full 10 watts on the lights. I'm not sure I got enough heat sinking in here for that. So we're limiting it, I think, to 3 watts. Also, if there's a software failure, it's not going to go to 10 watts through some software glitch. Over here, here's our potentiometer. This is where the wafer switch used to be, which simply turned on either the top or bottom lamps. So what we decided is just put in a potentiometer, turning it to the right, increases brightness on the top light, and then turning it to the left increases brightness on the bottom lamp, and that works pretty slick.
So there we have it. Now, I doubt if very many of you out there have a microscope that needs its lamps replaced. However, this is a demonstration of just how to do a project involving lights, dimmers, and mostly how to get a lot of mileage out of those little circuit boards you have made. So I hope you find this useful in your next project.